In past chapters, we have talked about naming molecules that have the root of their name as an alkane, alkene, or alkyne, and some aromatic molecules. We talk in this chapter about molecules that have functional groups that are listed as a suffix. The first part of a molecule is listed the same as before, except now we add a suffix that tells us about the most important functional group on the molecule. In most cases, the suffixes replace the E at the end of the molecule name, as seen with propanoic acid. In the case of nitriles, and only nitriles, the suffix is added with no other change to the molecule name. We can apply this into our general scheme that we have used for nomenclature before. We will find the highest priority group and name that first before we assign numbers. In the case of a molecule with a functional group suffix, the location number for the suffix needs to be as low as possible. So if we have a carboxylic acid, we need to make sure that that is numbered as 1, or if we have an aldehyde, we need to make sure that's numbered as 1, or if we have a ketone, we want to make sure that's as low as possible. The functional groups that end up as part of the suffix all have different endings to indicate their presence. For example, a carboxylic acid will replace the E from the root with oic acid, etc. I could go through and read these endings to you, but ultimately you're going to need to memorize the endings that go with each functional group that are listed in table 4.1 of your text. This is the first part of the table, and this is the next part of the table. I would note that, like in the functional groups themselves, amides and amines are easy to confuse, so pay special attention to make sure you can differentiate those. Many of the functional groups listed had 3 non-carbon atoms attached to the functional group carbon. The first time this shows up in a molecule, this is necessarily going to be the number 1 position, because 3 bonds to other things leaves only room for a chain of carbons in one direction. If we had another group like this, that would be at the highest numbered position. So we generally don't need numbers for those. Any additional 3 non-carbon based functional groups would need to be on a side chain, so we don't generally need numbers for those. Any functional group with fewer heteroatoms, things that aren't carbons, would likely need a locator to indicate position. Look at each of the examples shown to see that the position locator differentiates between molecules that are clearly not the same. So like 2-pentanone versus 3-pentanone, 2-pentanol versus 3-pentanol, and 2-pentamine versus 3-pentamine. We need those numbers to say the right molecule. When we have multiple of the same functional group, we don't drop the E at the end of the root, and we always indicate the number of functional groups with a prefix, just like we did with multiples of the same side chain. So for example, propane dioic acid is the correct name for a propane with 2 carboxylic acids. We left the E in there, and we don't need numbers. In many cases, we do need a number to locate each instance of a functional group, just like with side chains. The exceptions again are the functional groups with 3 heteroatoms, which are always at the end of molecules. The rules from table 4.1 get us most of the way, but acid anhydrides may not be symmetrical. In the event that an anhydride is asymmetrical, the 2 sides of the molecule are listed alphabetically, followed by the word anhydride. Esters follow an interesting convention for nomenclature as well. The ester is divided into 2 groups. The side of the molecule with the carbonyl, which is named like the anion of a carboxylic acid, a carboxylate, and these molecules, the carboxylic acid ending, has the ic acid or oic acid part swapped for 8. Think acetic acid and its anion acetate. This portion of the molecule is considered the main chain. The other part of the molecule, which does not have a carbonyl, is labeled in the form of a side chain as a separate word in front of the main chain and any modifiers. So we would name this an alkyl alkanoate. Here are some examples. We have an ethyl butanoate and a propyl ethanoate. It is easy to forget, but the functional group that's named needs to be on the part of the molecule that is named as the main chain. Sometimes this means that we have a shorter chain. That's okay, as long as we find the longest chain with our highest priority functional group or groups. So notice, with this carboxylic acid, there could be a chain of 6, but it wouldn't include the carboxylic acid. So instead, we need that chain of 5, and it becomes a 2-ethyl pentanoic acid. For this alcohol, we have a chain of 6, and it becomes a 2-ethyl 2-methoxyhexane 1-ol. This chain can only be 3 because it needs the amine on it, and the cyclopentyl group would be a side chain. And this group would be a ethyl 3-methyl 5-nitrohexanoate. Nitrogen, like oxygen, interrupts the carbon chain, so only things on one side of a nitrogen can be considered part of the main chain. However, nitrogen side chains are labeled like all other side chains, except that they're given the letter N instead of a number to indicate the side chain is located on the nitrogen. So in this example, we have the ethyl located at the N position, or in this example, we have NN diethyl locating 2 ethyls on that nitrogen, or in amides, we can have a similar type of locator, N-propyl propanamide, indicating a propyl group coming off of the nitrogen, or an N-cyclopentyl, indicating a cyclopentyl coming off of N, followed by an N3-dimethyl, indicating methyls at the nitrogen and at the 3 position. Just because we have higher priority functional groups at this point doesn't mean we can't have alkenes and alkynes. They are still named as part of the root, so we can have a propanoic acid, a propenoic acid, or a propynoic acid. However, alkenes and alkynes remain lower priority than all functional groups indicated in the suffix. So the functional group is given the lowest possible number, and the alkenes and alkynes fall wherever they happen to fall. So in this example, we have a 4-methyl pent 3-ene 2-one. The ketone is given the lower number. Try to identify the names of the following molecules as practice, and we'll go over those together. Next, we have a 4-nitrohex-5-ine 3-ol. So the alcohol is given the lower number preferentially, regardless of where the nitro and the alkyne fall. The next example will have the nitrile as the lowest number. This will be a 5,5-dichlorohex-2-ine dinitrile. And finally, a 4-ethoxy 5-ethyl hep-4-ene 2-ine al. If we have multiple functional groups that change the suffix, they cannot all be part of the suffix. Instead, these functional groups are listed as side chains if they are not the highest priority. Notice that all priorities 1 through 6 have 3 bonds to the more electronegative atoms. Some have conventions as side chains, but the instances where we actually need to use these as side chains for priorities 1 through 5 are rare enough that we'll ignore these for the purposes of this course. Starting then with nitriles at priority 6, we need to recognize the side chain prefix that is used when a higher priority group is named in the suffix. So if we have a carboxylic acid that also has a nitrile, we need to recognize that we're going to name that nitro as a cyano. Carboxylic acids are notorious for having common names. These names are often used interchangeably with the IUPAC name, or in the case of benzoic acid, replace the IUPAC name altogether. No one will translate these for you when you grow up, so you need to memorize these. The 7 highlighted in red are the most common, and those are the names of the monocarboxylic acids that I expect you to memorize. There are also a lot of dicarboxylic acids that are primarily known by their common names. You might recognize some of these names from the citric acid cycle. Others are particularly important as natural products or laboratory reagents. These too must be memorized. Along with the trivial names for the carboxylic acids themselves, we also give trivial names for the positions relative to the carboxylic acid. So the first carbon off of the carboxylic acid carbon is the alpha, then the beta, then the gamma, then the delta, then the epsilon, until finally, at the very end of the chain, we get the omega carbon. Examples of this type of trivial positioning system come through all over the place, notably omega-3 and omega-6 fatty acids, where we have the last double bond position given relative to the last carbon, the omega carbon, of an unsaturated fatty acid. Alpha amino acids, where the amine is the alpha carbon of a carboxylic acid, or beta-keto acids, a class of compounds abundantly common in biology. Any name derived from a carboxylic acid may also be derived from the common name. For example, the anhydride of ethanoic acid may be called ethanoic anhydride, or it could also be called acetic anhydride. And the amide of ethanoic acid can also be called ethanamide or acetamide. You can see examples of all the changes that may occur here. I'd also like to note that dicarboxylic acids can sometimes form cyclic anhydrides or cyclic amides. These are common when they could form 5 or 6 membered rings, and are just given by their common name with acid replaced by anhydride, or their common name with amide as part of the name instead of oic acid. So example here, we have succinic anhydride. Aldehydes also have common names derived from the related carboxylic acid. In each case, ic acid is removed and replaced by the word aldehyde. So what used to be formic acid when it's an aldehyde is formaldehyde, or propanoic acid becomes propionaldehyde. Ketone trivial names look a little bit more like ester trivial names. They're going to be named as ketones with 2 side chains coming off. If the side chains are the same, then the prefix di is used rather than repeating the name of the alkyl chain. Notice that in every case, the carbonyl carbon is not counted towards either chain. So the propanone is a dimethyl ketone, with 2 carbons accounted for by the methyls, and the last carbon is assumed as part of the ketone. There are 3 additional common names that don't follow this rule: acetone, which is propanone, benzophenone, and acetophenone. Each of those needs to be memorized. Alcohols also have a host of common names, but in these cases it is just the name of the carbons as a side chain followed by the word alcohol. Phenol is a specific exception where phenyl alcohol is further shortened to phenol. Phenol is the only accepted name for this compound, so it absolutely needs to be memorized. There are also a few common names that are beyond this form that are examples mostly interesting but not particularly useful, like wood alcohol for methanol, grain alcohol for ethanol, or rubbing alcohol for isopropyl alcohol. Most people who aren't trying to confuse you will use the IUPAC name or the common form of the common names rather than these more trivial names. Believe it or not, amines also have a trivial name system. Go figure. This works just like alcohols and ketones and ethers, except you have more alkyl groups. Just keep naming the side chains in alphabetical order until there are none remaining. The only additional name to memorize is aniline, which is the IUPAC name for an amine directly off of benzene. We have mentioned now several trivial names that are the only accepted IUPAC names for a molecule. Benzoic acid in that first row, and in the second row, benzaldehyde, phenol, and aniline. Notice that we'll also name all the derivatives of benzoic acid with benzoic acid as the root name. So benzoic acid, when it becomes an ester, is an alkyl benzoate. Or when benzoic acid becomes an amide, it's benzamide. Or when benzoic acid becomes a nitrile, it's benzonitrile. These structures take priority in nomenclature. If there are multiple groups that would be given a common name, the highest priority will be the one that takes priority for the name of the molecule. For example, you could have a 2-aminobenzoic acid. Benzoic acid would be the 1 position and would be named as a carboxylic acid rather than an aniline. But we wouldn't have a 2-carboxyaniline, so we wouldn't have the aniline be the primary name. We learned a lot of nomenclature here, but now we're done. Pat yourself on the back and start memorizing.